give you a small summary. So then we move to B.2. Because the concept is pretty abstract, so we need to understand very well. Oh, so yeah, thank you. Oh, a button, one button. Learn it. Yeah. I always. Yeah, because the previous instructor may use the laptop, so the connection is to the laptop, not the station. All right. Yeah, I need to check it next time. Yeah. So, oh, yeah. Too big. All right. So I want to clarify. So here, the two concepts. One is the dominant term. Second is the growth function. Yeah. Why we need to introduce these two concepts. Yeah. So here, let me do a small summary. Yeah. All right. So our goal. So what is our goal? What we are doing here, we want to do analysis of algorithms. So that's our goal. Okay. So we do analysis of algorithm. All right. Yeah. In order to do that, when we start, first we need to find the efficiency function. Yeah. The first step. Yeah. So here we jump to efficient function. Yeah, because I want to connect to these two concepts. So I do not talk about how to get efficient function. So that's, we skip that part. That's the problem solving, we do a lot of things. Our starting point here is, yeah, so let's say step 0, we have the efficiency function. Yeah. Efficiency. Efficiency function. That's our starting point. Okay? All right. Then, step 1, because usually the efficiency function could be relatively complicated. It contains multiple terms. Okay? Usually, efficiency function. Yeah. So now we do first round simplification. So the first round simplification. First simplification. So what's that? We only keep the dominant term. We only keep the dominant term. Yeah. There are multiple terms in the efficient function. So sum of multiple terms. So one function is represented as sum of multiple terms. So then we compare those terms and we pick the most dominant term. Yeah. What do you mean dominant term? Look at this formula. The dominant term, if you take the ratio with any other terms, just pick one, any other, you pick one. Dominant term over any other term, if you calculate the limit of that ratio, when n goes to infinity, it's infinity. This tells you the meaning of dominant. Okay? Yeah. The ratio goes to infinity. when n goes to infinity. That's the dominant meaning. Okay, mathematically, we understand in that way. Yeah. All right. So we only keep the dominant term and throw away all the other minor terms. Yeah. All right. That's the first round simplification. Then second round simplification. Okay, second round on the dominant term. Okay, yeah, all dominant. Make the coefficient 1. Yeah, dominant term. It's the coefficient of that dominant term may not be 1 in general, right? Yeah, 1/2, 2, some constant. Yeah, positive constant. Yeah, here positive constant. Because think about, how do we get the efficiency function? We count the number of basic operations. We count number of basic operations. That number must be positive number. No. So that's the reason our efficient function should take the positive values. Positive. So we do not consider negative values, because it's a counting number. Your counting number cannot be negative. No. No. All right. So how to second round simplification? Make the coefficient one. Okay. Make the coefficient of the dominant term 1. Okay. If you do that, that's a simplification step. If you do that, you get a growth function. Okay. So that's what we call the growth function. Okay, growth function. Yeah. Yeah. So that's a relationship. Dominant term, growth function. And you may ask me why we do second round simplification. Yeah. Yeah. Because remember the last time we talked about, so why we do this, we want to do characterization of our algorithms, right? Yeah. Yeah, because we want to put our algorithm in certain category, appropriate category. Okay, yeah. So the second round simplification is for this characterization. Characterization purpose. Okay, same category. Yeah. So that, let me further explain the category. That because we want to put it in a certain category. Some category here. Some category here. Okay? Yeah. What category? Remember the last time we look at the ratio F, that ratio, capital T of 2n over capital T of n, approximately equal to C, capital C of 2n over capital C of n. Okay? Yeah. So last time when we look at this expression, yeah, because these two functions, capital T function, capital C function, their differences only at the constant. Only at the constant. The constant cancel out. So here we say these two functions have the same increasing rate. Increasing rate. Every time we double the problem size, the ratio is the same. So we define the increasing rate as the ratio of the same function, but the numerator we use double of the original problem size. Denominator use the original problem size. So that's the way we define that ratio of the rate of increasing rate. Yeah. So last time, so because these two functions have the relationship like this. So we put them in the same category. Yeah. All the functions in the same category, they have the same increasing rate. The difference is only each function has different constant, different positive constant multiplier, okay? Multiplied by a positive constant. Yeah. That's the difference. Yeah. The constant you can change, yeah. But the shape, same shape, but yeah, because the constant is larger, for example, the same shape, yeah, okay? The function, same shape. The upper one has larger constant, okay? Larger constant. Yeah, let's say constant 3, constant 2, constant 1, constant 1/2, okay? Yeah. So these functions, they are in the same category. Yeah. But the difference is each function has a different constant multiplier, okay? Yeah. All right. Yeah.
So how did you get N2 as the growth function?
Yeah, 2n, that's the problem size. That's the problem size. Problem size. Yeah. So this is the way we look at how fast the function increases.
Wait, how did you get to learn the problem size?
Yeah. How problem? Yeah. All right. So do you mean how to why we use this 2, right? Yeah. 2, that's a convenient number, double. So when you double the size, how much the function value it becomes. Okay? Yeah. When you double. Although if you want to define triple, it's fine, yeah, but not as simple as double. Right? Yeah. So all right. So
Is there 2 terms?
not 2 terms. So here, the whole function. Here, the whole function. No matter how many terms it has. Okay? So here, we don't consider the terms. Here, in this definition, we just look at the function value. T function value. Yeah. You look at T function value. Okay? So you do not worry about the number of terms. Okay? Yeah. But if you worry about number of terms, the dominant term is the best representation. Because the minor terms, the impact so small. Infinity. So all the minor terms you can throw away comfortably. Because the impact is so little. You keep the ratio, infinity over 1. Let's say infinity over 1. Okay? Dominant term takes the infinity part. The minor terms, the 1 part. So you throw away 1 part. That's nothing, right? Yeah, that's nothing. So if you want to consider number of terms, you just use the dominant term. That's 1 term. Other terms, because when n is extremely large, other terms can be ignored. Last time I said, because we know infinity, all right.
But how does 2n over n relate to the 1/2 n squared minus 1/2 n?
You look at this function?
Yeah.
This function you can plug in 2n, all right? So this is a function, okay?
You can plug into n.
Right, plug into it. This is Cn, all right? So if you want to look at the C of 2n, you plug in, replace n by 2n. Replace n by 2n. That's how you calculate function of 2n. Yeah. Why 2? as I said, we want to look at the increasing. So you want to increase the size, but what's the size is the best? Yeah, so people feel we double the size. That's the most convenient way. We look at size increasing. Okay?
So what does the C of 2n over C of n fraction give you?
That fraction gives you our rate, increasing rate.
Oh, okay.
Yeah. Because that should be
It's different from the growth function.
different. That's different. The rate is different from growth function. Growth function, dominant term growth function, we can put growth function here. Because the growth function here, we say they are in the same category. So here, T function and the C function, they are in the same category.
Yeah.
Similar. Growth function,
T's and C's.
right, cancel out. So if we put a dominant term here and a growth function here, they are in the same category. That's a relationship. Okay. They could be, they're,
Wait, so the T thing is the growth function?
T is the response, its meaning is the running time function. T is not the growth function.
Oh.
So here, all right, we do not work on T, okay? Yeah, so if you look at a story, we do not work on the T. T, we work on C function, okay? We work on C function. T, not stable, so we work on the C function. When we work on C function, we do simplification twice, okay? The first time, we get a dominant term. Second time, we get a growth function. Twice. Simplification twice. Okay? Yeah. All right. Yeah. Yeah. So here, the summary, yeah. We spend a lot of time here because this concept, at the beginning, this concept, you need to have good understanding. Yeah. So then we can move to the next step. Yeah. Next step, we will study the growth function. Yeah. When you study the growth function, you do not feel, oh, the growth function is different from the original function. And if you do not feel comfortable about the difference, there is a difference. So here I tell you, there is a difference, but they're in the same category, okay? Same category. So if we study the function in the same category, so that's what we are doing. We do characterization. So we put our algorithms in appropriate category. That's what we are going to do. Okay? That's what we are going to do. Yeah. After we get a growth function, then we want to put our algorithm based on the growth function, we put it in appropriate category. All right? So that's we are going to do. Yeah. All right, next. Oh, yeah, my remote control. The next step. We need to go back. We need to do comparison. We need to compare growth functions. Which growth function grows faster? Which growth function grows slower? Yeah, we do comparison. Yeah. So this is a comparison, right? Yeah. So when we do growth function comparison, we use this way. Limit of the ratio of two functions, or two growth functions. Limit of the ratio of the two growth functions. We calculate that limit. That's how we compare. Yeah, so let me show you. B.2, compare growth functions. We use the example from our element uniqueness problem. Element uniqueness, method 1, method 2. So let us extract growth functions from these two methods. All right. Method 1, the worst case. So this is the efficiency function. So C function, efficiency function. We use C function, not T function here. Okay? C function. And method 2, also C function, worst case. Yeah. Efficiency function. All right. Each function has multiple terms, right? So if you do the expansion, each function you have multiple terms. Yeah. First, yeah, so 2 rounds simplifications. 2 round simplifications. Yeah. So here, if we write 1/2 n squared minus 1/2 n. Okay. Yeah. First round, we cross out the minor term. We only keep dominant term. What's the dominant term? 1/2 n squared, dominant term. First round, simplification. Second round, we cross out, or we replace the coefficient 1/2 by 1. So we get the simplified version. The simplified version, that's our growth function. The growth function of method 1. For the second method number 2, 3 terms. First, we need to pick the dominant term. Okay? Yeah. The dominant term already has the coefficient 1, so that's the growth function. So that's already the growth function. Yeah. So after this step, we extract 2 growth functions for those 2 methods. So next, we compare these 2 growth functions. Which one grows faster when n is very large? That's our question. Which one grows faster when n is very large? All right? Use the ratio to compare 2 growth functions. Limit of the ratio. All right? Yeah. Okay, so n squared over n log n. We take the limit when n goes to infinity. Then we do cancellation. Common factor n, numerator, denominator, we do cancellation. So then we need to calculate the limit of n over log n. Can you, here we need to use calculus. We need to use calculus. So the question, do you have any idea what's the limit? What's the limit? If we take the limit of this ratio of 2 functions based on the calculus, what's the limit? Calculate knowledge.
0.
Which n is larger or log of n is larger? Log of base 2. So here, as I said, in our computer science, the default log of base is 2. Okay? So here you can use log 2. Later we can use a general log base, a greater than 1, general log base. Yeah. All right. So if you use log base 2, is n larger or log base 2 of n larger? If you do not know which one larger, when n equals 1024, that is 2 to the 10th. What is the log base 2 of n? Equals 10. So which one is larger? N is 1024. Log base 2 of n is 10. Which one is larger? So you get an idea, right? Much larger, right? Much larger. 1,000 to 1, that ratio. More than 1,000 to 1 ratio. So here you get an idea. The numerator is much larger than the denominator. That idea. Okay? All right. Yeah. So here, yeah, if we use the general log base a greater than 1, yeah, more general. So we want to look at this limit. All right. the answer is infinity. Not just large, but when n goes to infinity, the ratio also goes to infinity. Yeah. How to see it? Yeah. I want to convince you. Yeah. Because to most of you, you may not feel it's a simple answer, right? So you want to see why it is infinity. Yeah. So here, let me use two ways to convince you it's infinity. The first way, we use variable substitution. Yeah. Yeah. Why we use variable substitution? Because the log function, most of you may not be familiar with log function, right? When you say log function, you do not have the sense. Yeah. Yeah. Log function, it looks too complicated for most of you. Okay. Yeah. So we want to avoid log function here. Okay. So how to avoid log function? Let us introduce a new variable u. Let u be log base a of n. With this new variable substitution, the log is gone. We do not have the log. Okay? So log base a of n becomes u variable. Okay? All right. Then, by the definition of logarithm, we can write n equals exponential function a to the u. Exponential function. N becomes exponential function a to the u. Then the ratio becomes a to the u over, a to the u, right, over u goes to infinity. Yeah. Yeah. We know, yeah. When n goes to infinity, u also goes to infinity, right? Yeah. When n goes to infinity. Log base a of infinity must be infinity, right? Yeah. So u goes to infinity, all right? Yeah. Now we look at the new ratio. This time, the numerator is an exponential function, a to the u, with a greater than 1. With a greater than 1. Denominator is a u. We know it's a special polynomial. So numerator, you have an exponential function. Denominator, you have a polynomial. Have you heard of people always talk about exponential function always increases much faster than polynomials? Yeah. In our everyday life, people talk about something has exponential increasing rate. Then it means very fast. Exponential increasing rate much faster than polynomial increasing rate. Okay? Yeah. So that's the, people always say exponential function dominates any polynomial. Now how to see it? Later, I will use rigorous math to prove it. We will prove it later. So here, I just point out in our daily life, people has the experience like that. People talk about exponential rate. That means something, duplicate very fast. Exponential rate. Not a polynomial rate. Polynomial rate, not as fast as exponential rate. Yeah. Here we use that fact. Okay, all right. Yeah, next, math proof rigorously. Yeah. Now, I need to give you the rigorous math proof. I do not require you this math part in assignments. In our assignments, I will not give you math proof questions. Yeah. But we need to derive a few important results. So we need to use this math tools to derive a few very important results. So I want you to know how to derive those results. Okay? Yeah. All right. Method 2. Yeah. L'Hopital's rule. So here, the method 2, I want to convince you. Yeah. Yeah. Exponential function dominates polynomial. That's one. Another, n over log of n, that limit goes to infinity. Yeah. So these two things are equivalent. Equivalent. Yeah. But we use this calculus. Calc 2. Yeah, this is a Calc 2. In Calc 1, you do not have this result. Calc 2, this method, L'Hopital's rule. Okay, all right. Yeah. So what's the L'Hopital's rule? When we calculate the limit has the form ratio of two functions. Ratio of two functions. Yeah. So that's what we are doing here. Yeah. So based on the L'Hopital's rule, yeah, we can calculate the ratio of two derivatives of those two functions. That's a powerful tool. L'Hopital's rule is a powerful tool to calculate limit. Otherwise, if you do not use L'Hopital's rule in this situation, it could be very hard. Okay? So very powerful tool. Yes. So here, we use L'Hopital's rule. But L'Hopital's rule, before you apply it, you need to check the condition. Yeah. If the condition is not right, you cannot apply the L'Hopital's rule. Okay? The condition must be right. So what's the condition? The condition is the ratio should take the form called an indeterminate form. Indeterminate form. If the ratio is not an indeterminate form, then you cannot apply the L'Hopital's rule. What's the indeterminate form? So here, there are several indeterminate forms. In this class, we only use the first indeterminate form. Infinity over infinity indeterminate form. Infinity, the top infinity means the numerator function goes to infinity when n goes to infinity. That's the top infinity. The bottom infinity means the denominator function goes to infinity when n goes to infinity. That's the meaning, yeah. So we use the short notation, okay? Infinity over infinity. So this is a special notation, okay? This is a special notation. Do not treat this representation as a number, okay? Yeah. It's not a number. This is not a number. Infinity over, first we know infinity is not a number, right? Infinity is not a number. It's not a valid number. Infinity is a symbol, not a number. Infinity has certain definition. Yeah. We know its meaning, but it's not a valid number. Okay, we do not treat it as a number. So infinity over infinity, it's not a number. But we use it as a form to represent some special situation. Yeah. Infinity over infinity. Yeah. And it is indeterminate. Yeah. Because if you look at the possibilities of this infinity over infinity, how many possibilities, if two functions, you look at the ratio of two functions, both goes to infinity, the ratio of those two, how many possibilities do you have? First, could be infinity, right? The top function over bottom function could be infinity. That's the first possibility. Second, the ratio could be constant, right? The top function, bottom function, after you take the ratio, then it's a constant. So the second possibility. Third possibility, the top function over bottom function could go to zero. Yeah. So there are many different possibilities. That's why we say indeterminate form, not determinate. Many possibilities, so it's indeterminate. So we call indeterminate form. Yeah. Some students ask me, are there other indeterminate forms? Yes, there are many other indeterminate forms. For example, 0 over 0 indeterminate form. Yeah. The numerator goes to 0. Denominator goes to 0. Okay? It's also indeterminate. Yeah. Another one, 1 to the infinity. That indeterminate form. 1. Okay? The base goes to 1, all right? But the exponent goes to infinity. Indeterminate.
Most of 0 to the power of 0.
0 to the power of 0, that's not 0 to infinity. Oh, yeah, 0 to 0. Yeah, 0 to infinity. Yeah, 0 very small. Yeah, 0 to 0. Yeah, you're right. Yeah. And, right. And 0 times infinity. That's one. 0 times infinity. Okay? What's that? You know, yeah. So there are many other different, but for this class, only this one makes sense. Based on our efficiency functions, we only have the first form. We do not have other forms. Okay? We do not have other forms. Yeah. All right. Yeah. Yeah. Now let's look at how to apply L'Hopital's rule here. Yeah. All right. First, we check it's infinity over infinity indeterminate form. So it's legal to apply L'Hopital's rule. All right. Then we take derivative. The derivative of exponential function a to the u, we find this formula. Okay? So you know, look on web or some calculus book, yeah, find that formula. Okay? This is the formula. Natural log of a. Yeah. Remember, a is greater than 1. Okay? A greater than 1. Remember that condition. Okay, all right. Denominator 1. Yeah. A greater than 1. So natural log of a is a positive number. Yeah. When a is greater than 1, so any log function is positive number. Okay? Yeah. Here it's a positive constant. Then a positive constant times exponential function a to the u, when u goes to infinity, it must go to infinity. So the answer is infinity. So by L'Hopital's rule, we find this limit when u goes to infinity. Okay, all right. So that's the first way. Yeah. So we calculated, yeah, based on L'Hopital's rule. Okay. Yeah. All right. So this is our first result. All right. Then, yeah, I also need to talk about when we take a limit, we should be careful. When we take a limit, we should be careful. Why? Oh, sorry. Here we take derivatives, right? We take derivatives. When you take derivatives, you should be careful. Yeah. So here I want to show you. In your mind, yeah, in order to maintain the rigor, in order to maintain the rigor of math computation, you need to make sure each step is legal. So here, how do you know your derivative step is legal or not? Right? Yeah. You need to make sure your derivative step is legal. Okay, when you take the derivatives. Yeah. All right, so here, let me use this example to show you how to make your derivative step legal. All right. Do you still remember the definition of derivative? Recall calculus, what's the definition of derivative? First, there is one phrase description of the derivative, rate of change. Derivative means rate of change of a function, right? Yeah. Rate of change of a function. How to calculate rate of change? Rate of change of a function. Here, let me write. Rate of change. That's the meaning of derivative. Okay? But how do you calculate the rate of change? Right? Yeah. So you look at a function, you increase the function by delta x, small amount, delta x. Then you look at the change. When you increase the variable by delta x, the function value should change a little bit, right? Change, okay? Yeah. Rate of change means over delta, okay? That function value change over the variable change. Yeah. Numerator function value change. Denominator the variable change. All right? Yeah. The rate of change, and you take the limit. Delta x goes to 0. This is the definition of derivative. Okay? We use prime, f prime of x. That's the definition of the derivative. Okay? All right. You need to make sure this step is legal. All right? The derivative step is legal. Then you can apply derivative. Now, look at this function. The numerator function, denominator function, numerator function n, denominator function log of n. Do you know these two functions have derivatives or not? There are two functions. We want to see if their derivatives exist or not. So the answer is their derivatives cannot be defined. Why? Look at the variable here. Look at the variable here, n. What values do we take on n? N variable. 1, 2, 3, 4, 5, 6 positive integers, right? Can you take 1.5? And can you take 3.9? You cannot. And cannot take non-integer numbers. Okay? So here we call the variable only take discrete values. So here, only take discrete variables. So here, these two functions, they have discrete variables. Then the derivative does not exist for discrete variables. Because here you add a delta x, then for discrete variable, it's nothing. Right? You add a delta x it's not another discrete variable, right? So this definition does not apply on discrete variables. Okay? No. So you cannot apply this derivative concept on functions with discrete variables. All right? So that's why you should be careful. All our functions. So in this class, all our functions with discrete variables. Yeah. N squared, let's say n squared. N squared, this function, because n you can only take 1, 2, 3, 4, 5. Right? You cannot take non-integer numbers. Okay? So it's a discrete variable. Yeah. all the functions we use in this class with discrete variables. Okay? Yeah. All right. Yeah, so here, this step, you cannot apply derivatives directly, but we can apply indirectly. In order to apply L'Hopital's rule, we need to convert our functions to functions with continuous variables. Continuous variables. Let me convert it. Okay? All right. How about we switch to the corresponding continuous version of the functions and its corresponding continuous version x. And when we switch from n to x, we allow x to take all the continuous values. Okay? Yeah. This time, we do not require positive integers. All real numbers, or positive real numbers, we can say. Okay? Yeah. This time, continuous variable. Yeah. After we switch to the continuous version, then we know their derivatives exist. So it's legal, we can take derivatives. We can apply L'Hopital's rule. All right? Yeah? So this step. All right. So then we take derivative. This time we take derivative. Numerator, the derivative is what? Denominator, derivative of a log function, log base a, is 1 over natural log of a times x. Yeah. So you can, find it somewhere. All right. After simplification, you get a limit when x goes to infinity, constant, natural log of a. It's a positive constant. Okay? So this is a positive constant. Positive constant multiply that x. X goes to infinity, so the whole function goes to infinity. So the limit is infinity. Yeah. But this is the ratio of continuous variable version. X continuous variable version. Yeah. But our goal, what's our goal? Our goal, we want to calculate the limit of the discrete variable version. That's our goal, right? Our goal is, here we change it. We change it to continuous variable. But it's different, right? Yeah. So we need to go back to our discrete version of the ratio. Now, we go back to the discrete version. Okay? All right. When we go back, since the continuous version, the limit equals infinity, can we say the discrete version, its limit also infinity? Can we say that? Here, we know the limit of their continuous version is infinity. Can we conclude the limit of the discrete version also infinity? Answer is yes. But I need to explain why. The answer is yes, this step is legal. Okay? Yeah, so we get a continuous version limit. Then, when we go back to the discrete version, we have the same limit. Same limit. But the question is why? Why the same limit? Okay? Yeah. To answer this question, we need to recall the definition of limit. What's the definition of limit? Recall a little bit. Recall. Yeah. Right. Yeah. So approaches, right? Approaches something. So here we the variable approaches to infinity. Then the function, yes. So we can treat this whole function as a whole function. The whole function takes certain limit. Okay? Yeah. Takes certain limit. Yeah. So here I do not I do not need you to give me the whole definition. Okay? Yeah. We don't need that. We do not need to, So here I want to let you be aware of the one property here. When x approaches infinity, do you know how does x approach infinity? Do you know that? Here we say x approaches infinity. The question is, how does it approach infinity? Do you know that? How? Because there are many different ways to approach to infinity, right? When you go from one place to another place, you have many ways. When you go from here to Chicago, you have many ways. Here I tell you, go to Chicago. I didn't tell you which way to take. Here, the same thing. Here I tell you, x must go to infinity. Well, I do not tell you in which way. So in our limit definition, we do not say which way to take to approach to infinity, right? We never say that. In our definition, we never say you have to do certain way to infinity. We never say. If we do not say, what do we mean? If we do not say what way to take to infinity, what do we mean? It means any way is legal. Okay? Any way is legal. Is it based on our language understanding? If we do not say which way to take, any way is fine, right? So you can take any way approaches to zero. Okay? Yeah. For example, so here, x approaches zero. Can you take x 1.2, 2.3, 3.4, 4.5? I use this way to infinity. Is that okay? Right? Can I take it this way? 1 square, 2 square, 3 square, this way to infinity. Is that okay? Right? 1 cube, 2 cube, 3 cube, this way, x take this way to infinity. Is that okay? Legal, right? All legal, right? Yeah. Based on our limit understanding. All these different ways for x to approach to infinity, all legal. Then, how about I take a special way? This time here, I take special way. 1, 2, 3, discrete value, 4 to infinity. Also legal, right? That's the reason we can go back to our discrete version directly. Based on the definition of limit, it's legal. Okay? Yeah. Try to understand. Try to understand the logic. Yeah. I do not ask you to do the same thing. Yeah. Here I ask you to understand, all the logic behind our results. Okay? Yeah. Then you just apply our results. Yeah. The reason is, if you have good understanding, you can memorize the results better. Okay? If you understand the story behind the results, you can memorize the results better. If you do not understand, the results just like abstract symbols. That is hard to memorize, right? Yeah. So that's the reason. Yeah. All right. Yeah. So we get this result. Yeah. So the conclusion, after this comparison, after this one, the comparison, the growth function of n log n, the algorithm, okay? If the growth function grows slower, the algorithm will be faster, right? If the growth function grows faster, the algorithm will be slower. Okay? Yeah. So our conclusion is, our method 2 with this growth function, because this growth function grows slower than n squared, That means algorithm 2 is faster than algorithm 1. That's the conclusion. So for our element uniqueness problem, we know if we do the sorting first, we can get a better, we can do faster. If we do sorting, after this comparison, we know our algorithm 2 is faster than algorithm 1. Okay, yeah. So that's the conclusion of element uniqueness problem by this limit result. We have this, we just proved the limit result. Okay, all right. Introduction of asymptotic notations. This is the key concept of our module 2. Our module 2, the most important concept we need to learn in module 2 is asymptotic notations. Yeah. All right. Oh, yeah. Why I talk about the example? Oh, yeah. Oh, sorry. I jumped to a different part. I should be, I should start at the very beginning. Yeah. The beginning is C.1. Yeah, introduction to asymptotic notations. Yeah. All right. So then, yeah. Here, let's continue our discussion from limits of two growth functions. Now, let's look at when we calculate the limit of the ratio of two growth functions. Let's use the f function, g function to represent two growth functions. When we calculate this limit in general, how many cases do we have? The limit result of this limit. How many cases? Here I give you these 4 cases. First, limit equals 0. Okay. Yeah. Second, limit equals a non-zero constant. See non-zero. Yeah, because for this class, our growth function is supposed to take positive values, so the C constant also should be positive. Yeah. Because we only look at the ratio of two growth functions, two positive functions. Yeah. So C should be a positive constant. Yeah. Then the limit could be infinity. Yeah. Then the 4th case, the limit does not exist. Yeah. The 4th case, other here. So what do you mean other? So the limit does not exist. No. It's not guaranteed that limit always exists, right? Sometimes it exists, sometimes it does not exist. Yeah. So we should consider that case. The limit does not exist. Okay? Yep. All right. Yeah. So these 4 cases. Then, when we have these 4 cases, now we want to describe which growth function increases faster, which growth function increases slower. We want to describe, because as a comparison result, we want to know which one increases faster, which one increases slower. So we want to use some concept to describe it. We need to use a special concept to describe how fast a growth function grows. Yeah. All right. So the first case, the concept we want to use is the order of growth. Growth in certain order. Now, we know a function, yeah, so all these functions grow, yeah, but some functions grow with higher order. Some function grows with lower order. Yeah. So we use a abstract concept, order of growth. So you may ask me, what's the order of growth, right? Yeah. So let me delay a little bit, okay? Let me delay a little bit. Yeah. But I will let you know at the beginning of next class, okay? Yeah. Yeah. So here we just imagine there is an order of growth concept. All right. So if case 1, the limit of f of n over g of n, if the limit equals 0, then we say our conclusion is because we know f function grows slower than g function. So based on our intuition, we can say the order of growth of f function is smaller than the order of growth of g function. So what's that order of growth? Yeah. I will give you the explicit description next time. Yeah. Not this time. Today we do not have enough time. So I delay it. Okay? Yeah. So we have this inequality. Okay? A comparison. Compare the order of growth of these two functions. All right. Case 2, C, constant C. Yeah. Remember, if the ratio is constant C, these two functions should be placed in the same category. If they are in the same category, can we say they have the same order of growth? Yeah. Right? Because same category. Yeah. So we define, they have the same order of growth. So case 2, yeah, we say these two functions, they have same order of growth. Okay? Yeah. Case 3, yeah, opposite to the case 1, the order of growth of f function is greater than the order of growth of g function. Yeah, because f function increases much faster than g function. So the faster means the order of growth is larger. Yeah, based on our intuition. Yeah. So we have the first 3 cases. We use order of growth. We can describe using inequalities. 3, yeah. Second one is equality. So inequalities or equality. These 3. Yeah. All right. But case number 4, then we don't know how to say about order of growth. Case number 4, the limit does not exist. Okay? So we don't know what to do. Yeah, limit does not exist. So that means we cannot get any information from the ratio. Yeah. So for case number 2, we need to find a different way to compare these two functions. Because the limit way does not work. The limit way cannot provide us any useful information. So we need to look at some non-limit way to get more information, useful information. Case number 4. Yeah. So that's another important part we need to do. Yeah. Yeah. All right. Then, yeah, we have a few minutes. So then, the last thing, to represent the first 3 cases. 3 cases, because we have good descriptions. Equality, inequalities, we have good descriptions. So we want to use some compact notations to represent the first 3 cases. Compact notation. Because these 3 represent still too long, right? Not compact. Okay? These 3, equality, inequality, too long. Okay? Not compact notation. So we introduce asymptotic notation here to represent these 3 different cases in a very compact way. So what's that? The first case, we say f function belongs to little o of g function. This little o. What's the meaning of this little o thing? The limit equals 0, okay? So if you see limit equals 0, then this little o notation. If you want to understand what's the meaning of this little o thing, you go back to this limit. The ratio of f function over g function, the limit equals 0, where n goes to infinity. Okay? Yeah, that's the meaning. All right? Second, asymptotic notation. Yeah. The ratio limit constant c, we say f function belongs to capital theta of g function. Capital theta, another asymptotic notation. All right? The third, f function belongs to little omega function. Okay? Little omega g function. So you connect to this limit is the infinity case. But notation is short. Okay? Math notation is short. We do not need to write a lot of words. Okay? So we use this very abstract asymptotic notations, and we mean that, you know, the limit means, the meaning behind it, asymptotic notation. The meaning is clear, but we don't want to say a lot of things. Okay? Yeah. Yeah. So we introduce these 3 asymptotic notations, and we have 3 more next time. 3 more next time, asymptotic notations. All right? Yeah. So let's continue this topic next time.